All right, let's get it started. All right, so first I need to apologize a little, again for the wait operation on the semaphores. Last class I inadvertently said like a couple of times that wait operation would do increment, but obviously that's wrong. So wait is like the process wants to acquire a resource, so the wait will decrement the semaphore. Um, so and um, so before I start today's lecture, I really wanted to say, in my opinion, out of all the main topics we are covering in this course, the processes, threads, virtual memory paging, synchronization, file system, and I/O. The topic that we're discussing right now, the synchronization, is probably would be used the most in an interview, actually, for a computer engineer. The synchronization is actually very popular in interview questions. As a matter of fact, that I heard a good story about a newly graduated undergraduate from SDSU. Um, she solved a semaphore coordination problem in her job interview. Because of that, she eventually got the job. So she did very well in a semaphore related question in her interview that none of other applicants were able to answer correctly. So that student was really happy that she did the programming for the producer consumer problem you guys are doing in your assignment 5. Yeah, I guess that's just because the synchronization problems, they are almost everywhere in today's software systems. So you guys need to realize how important it is for as a computer engineer or computer scientist. You need to know this stuff very well because in today's computing, we're always talking about multi-threaded or multi-process kind of computing environment in a multi-core kind of a world. All right, so okay, so so last time, we introduced the semaphore concept as a programming construct for solving synchronization issues. So we went through this producers consumers problem using semaphore as a solution to that problem. So here we need we need 3 semaphores, right? One for tracking the resource allocation for the empty spots in the buffer for the producer, one for tracking the number of elements in the buffer for the consumer to consume, and we also need a mutex, right, to protect the access to the shared buffer. Now that mutex needs to be used for protecting the concurrent access to the buffer between the producers, and we need to protect the access to the buffer between the producer and consumer, as well as that mutex. That mutex also needs to be used to guard the shared access to the buffer among the consumers, right? So anytime the buffer is being updated or being read, right? That buffer needs to be protected. All right, so And so last time we briefly at the end of the class we talk about a possible deadlock scenario if we switch the order of the oops. So here this is the consumer function. So here the consumer needs to first acquire an element from the buffer, right? Meaning the unconsumed. Sorry.
We can't see your screen.
Oh, well, actually, so for you guys can't see the screen? Oh.
No, it's
sorry.
just right now.
Okay. Maybe let me see here. Oh. Thank you, Amy. Is that Amy? Yeah. Oh, my apology. Yeah, so now can you see it?
Yeah, we can see it now.
Oh, okay. So I've been talking without showing you guys the PowerPoint. My apology. So, all right. So yeah. So I was let's just go back a few slides here. But for what I just talked, you guys all understood, right? For what I just talked, so I won't go through them again, I guess. But anyway, so let's see this consumer method that we talked about in last class, right? So, so a potential deadlock scenario here is that if we switch the order of the wait operation here and the mutex here, we could end up with potential deadlock, right? Why is that? So let's do this. Let's walk through this again, because I think this is important. So let's say we do this, right? So the consumer comes in, then you will first acquire a mutex, the lock, to access the shared buffer. But if consumer does this first, right, and then the consumer will try to decrement, right, the unconsumed semaphore, right, to acquire an element from the buffer, right? So what's going to happen? So let's say everything starts with an empty buffer, right? So so after the consumer acquires the lock here, right? After that, none of the producers and other consumers can access the shared buffer, right, anymore, because it's being guarded now by this mutex. And then the consumer will try to consume something from the buffer. Obviously, the buffer is empty, right? So the consumer can't really consume anything from there. So the consumer will wait, right? The first consumer, because there's zero element from the buffer to consume. So, but the bad thing about this is while the consumer is being put to sleep and wait for an element to be produced, the consumer is put to the sleep with what? With this lock, with this mutex lock, right? And because this mutex lock is being held by the consumer, by the first consumer, then the producers can't really enter the critical section to put any element there, right? So the producer, because the producer needs to acquire the lock to enter the critical section, so that the producer can put an element to the buffer for the consumer to consume, right? So the producer will be blocked, but this consumer is also being blocked, right? So this is a deadlock situation, all right? So everybody gets what I'm trying to say here? This is important. Yeah. Okay, let me open that. Oops. Okay. Why I'm not seeing the chat window? All right, okay. Nonetheless, I assume you guys, yeah, okay. So let's look into the actual implementation of this the semaphore operations. Okay, so again, the down operation or the wait operation, the implementation is like this. So first, you would decrement. It would try to decrement the semaphore integer value, right? And after the decrement, if the semaphore integer is less than 0, that means what? That means you actually you don't have any resource to acquire. So then the process or thread will be blocked, and it would be put onto a wait queue. So that's the wait or down operation, right? And this is the up or signal operation. So first, it would increment the semaphore, and so if after incrementing the semaphore value is still less or equal to 0, that means what? That means you actually have something waiting on the queue, right? So this part is a little confusing, actually. I want you guys to understand this. So if after incrementing the semaphore value, if that value is still less or equal to 0, that means you have something, you have some processes or threads that are actually waiting for the semaphore. So in that case, you would do what? You would bring one thread or process from that wait queue and bring it back to ready. Okay? You guys understand what I'm talking?
Yeah.
Okay. All right, cool.
Is this wait queue a
get
queue
it.
that you have to set up, or is it something that the
Oh
system
yeah,
has?
yeah. It's a part of the operating system implementation. Operating system maintains the semaphore operations, and yeah, the wait, the down and up operations on the semaphore. Actually, they are part of the operating system implementation. All right. So this queue is also maintained by the operating system. All right, good question, Eric. All right, so
question with regards to it with the program for assignment 5.
yeah,
So we use the semwait and whatever the other one is. That's calling that library that deals with connecting with the operating system. Handle all that then.
Yeah.
Okay.
Oh, you mean sorry? Yeah. Oh, the POSIX. Are you talking about the POSIX methods?
Yeah.
The same wait and same. Yeah. So those two options, those two methods. Sorry, from the POSIX library. Yeah. I mean, eventually.
That library. I'm sorry, and that library is actually what's calling the operating system to do all of this up and down
Correct.
and use stuff. Okay.
Correct. Yeah.
So we just use the POSIX semaphores. We don't have to actually implement this ourselves, right?
Yeah. Yeah. No, you don't.
Okay.
Yeah. This is not. Yeah.
I got
If you
scared.
can implement this, that would be nice, actually. So it's actually, even these two operations, they look very simple. It's hard. It's hard to implement these. Because of what? Actually, you guys are asking very good questions here. Because these two operations, they need to be what? They need to be atomic, okay? So all these, you need to guarantee this down operation here, all the instructions, all the code inside this method, they need to be executed atomically, okay? So that's because you can't switch this execution. You can't switch out this execution, at any point. You cannot interrupt this operation. Otherwise, all the states of the semaphore would be compromised. The data integrity cannot be guaranteed there. The same applies to up, right? So these two operations, they have to be executed atomically. So actually, that would be a good segue for what I want to talk next. Is that, yeah? So the proposed implementation, these they're not atomic. So possible solutions. So we could, during executing those two operations, we could disable interrupts. Or we can use the hardware support, test and set lock we just talked about last class, to guard that piece of code. Okay, and specifically about disabling interrupts, that kind of approach would only work for in a uniprocessor environment, okay? Because if you have multiple cores or multiple processors, you could have interrupts for each CPU, right? So in that scenario, in the multi-processor scenario, we need to use both disabling the interrupts, and we also need to use critical sections there to accomplish atomicity there. So, all right, so we won't get into that. We just assume that the atomic execution of these two operations, they're handled by the operating system and hardware support. All right. Okay, so last time I also briefly went through this this implementation of using test and set lock to achieve sort of a minimal weighting. Okay, and also here if the thread is blocked, we want to put the thread to sleep. But here I want to make sure you guys understand that when you put the thread to sleep, we have to also make sure that that step is also executed atomically. Okay, so when we put the thread to sleep, we have to make sure it goes to sleep. Okay, because later on, we will try to wake the thread so that the thread can be put back to ready queue to continue execution. So what I mean here, we need to put the thread to sleep atomically. I mean that you want to guarantee that while you're putting the thread to sleep, that operation itself cannot be interrupted. Okay, you want to make sure it goes to sleep. Otherwise, if during, say, right before you put it to sleep and the whole thing gets switched out, and that could happen, right? And then later on, you send the wake to wake that thread for execution because it wasn't put into sleep, and so you can't really wake it up for execution. So I just want to make sure you guys understand that you know, all these so at, you know, some code in this in the synchronization context, you need to make sure that the code needs to be executed atomically. All right. Okay, so so we talk about 3 use cases about using semaphores. You know, the simplest case was you know, using semaphore as a mutex, right? Meaning you only have 1 unit of resource or 1 permit of resource, and you use that as a lock to accomplish a lock kind of implementation. That's what we call binary semaphore. And also we talk about the counting semaphore as a sort of a resource allocation mechanism. We talk about that in the producers and consumer problem solution. There is also a third use case is that the semaphore can be used to enforce sort of scheduling or precedence constraints. So we want to walk through some examples of that. So let's see here for a quick example here. So actually, I also briefly talked about this case in the last class. So here, if we want to make sure, so here we have 2 processes. If we want to make sure process B, if we want to guarantee process B to be executed before process A, right? How are we going to do it, right? How are we going to do it? So we could set up a semaphore with initial value as 0, right? So in the process A, it would call wait or down operation on the semaphore, right? In the process B, it would call signal or up operation on the semaphore. So with this simple setup, actually we can force the order of execution between these 2 processes, right? Why is that? So if you execute process A first, process A will be what? You start with the semaphore initial value as 0. So process A will, you know, will call this down operation. It will decrement the semaphore. The semaphore value becomes less than 0. So process A will be blocked, right? Until, assuming you only have 2 processes. So process A is blocked until what? Until process B gets executed, because process B will increment the semaphore, and then process A will be unblocked, right? So so if you try to execute process A first, it will be blocked. It will have to wait until process B to be executed to unlock process A. So if you just execute process B first, right, and the process B will do an up or signal operation, then the semaphore value will become what? Become 1, right? Will become 1, and then you execute process A. It will not be blocked because the semaphore value is 1. You decrement that value to 0. It is still not less than 0, so process A will not be blocked. So either calling sequence, either you call process A first or you call process B first, the order of execution is kind of enforced, right? That scheduling constraint is sort of guaranteed, that you will guarantee process B will be executed before process A. All right. Now this is related to actually your assignment 5, right? In your assignment 5, you need to produce, like, you can only produce 100 candies, right? After you produce 100 candies, you have to wait for all the candies to be consumed, right, before your main thread can exit, right? So how do you enforce that wait, right, of the main thread waiting for the consumers to consume all the candies before the main thread to exit? So you can use a semaphore like this to achieve that. Clear? Give me some response. Yes? Okay.
So you're saying to use a semaphore, would have multiple semaphores, and one of them would just be saying that the system is not taking any more production, and that's how you would do it, or I'm misunderstanding what you were.
Oh, I'm just talking about, yes. For you to set up a thread to wait for other threads, right? You could use semaphore for you could use what I just talked about. We can get into the details about how to use this for assignment 5, maybe in office hours. All right, but this is a way for you to set up one thread to wait for other threads, right? Are you are you understanding what I just talked about this?
Yeah.
Right. Okay. So that's good. Okay. All right. So let's walk through another example of this here. So let's say, we have more threads in the system, or processes in the system. So we want process A to wait for all of these processes in BCD. How are we going to do that?
Don't you isn't that when you join?
Yeah, well, join is, are you talking about the thread join? Yeah, that's the POSIX thread join. Yes, you can use that to achieve the wait, right? But here, if I'm talking about using semaphore to do that. So how can you use a semaphore to enforce the order of execution here between process A and the processes B, C, D? So let's say you want process A, right, to wait for BCD to finish before process A can continue its execution. How do you do that using semaphore? Anybody can give me a quick idea? So we just talk about like two processes, right? Like process A waiting for one process, but now process A has to wait for 3 processes. How do you do that? Anybody? This may show up in your interview. Come on, guys. Give me a try. No? So process A has to wait for what? For all these other processes. If you use a semaphore to control the order of execution, how are you going to do it? Come on, guys. Are you guys typing something in the chat window? Maybe
The order between just the children as a group versus the single parent, or the order
No,
of.
they're not sure. Like let's say no, process A is not necessarily apparent to these processes. Let's say they're just they're on the same level. They're not process A here is not the parent of BCD, or it could be the parent of BCD. Doesn't matter. So, but you have 4 processes being executed at the same time here. So how you gonna force the execution of A, right, to
So
be
if
after?
if we're using the semaphore, semaphore is a counter, right? Or it's an integer.
Yes.
So couldn't we just, since we're gonna wait on 3, make the semaphore decrement by 3, and then once they're done, once each one finishes, so let's say process B finishes, you would make that one increment the semaphore just by 1.
Yes.
And then the next one finishes. So
you got it, Frankie. Thank you. Thank you. Yeah, that's exactly right. So, which is the next slide. That yeah. So exactly as you just said, Frankie. So for process A, if you're only using one semaphore, so there are other solutions, okay, to this scheduling problem. So you could use 3 semaphores, right? BCD, each one of them has 1 semaphore. But here, let's assume we only use 1 semaphore. So you initialize the semaphore value to 0, and then yes, so when you execute process A, you decrement that semaphore 3 times, right? And in BCD, each one of them increments the semaphore 1 time, right? So so you can see the process A can only continue its execution after what? After all these processes, BCD, increment the semaphore, right? Excellent, Frankie.
I have
all
a
right.
question.
Yeah, go ahead.
Like, how do we know if all 3 of them executed, or like one of them executed like 3 times?
Oh, you mean how do we know process B executes the semaphore?
No, so like if like process B executed 3 times, it like semaphore would still become 0, right?
Oh, you mean you want to execute process B 3 times, but just for one process. You want to increment the semaphore there for 3 times. Yeah, sure, that can, but here, this is just one possible solution. Yeah, so here we just increment semaphore 1 once for each for B and C and D, and so that well, this is your code, right? You can do that, right? So say in your code in process A, you do decrement 3 times, and then in process B you increment the semaphore once, and process C you also does the incrementing once. In process D you also do that once, right? This is your code. You can choose to do that, right? And that would be a solution to ensure the order of execution of A to be after BCD. Does that answer? Yeah.
What I meant is, so let's say we have like everything set up like this, but so instead of like let's say I executed B and then C and then B again, so semaphore would become like 0 and A would think it should go when.
Well, that's a good, yeah, that's a good thought. You're saying that process B gets executed twice, right?
Yeah.
Or maybe you could your scheduling, you could execute B. You say, well, I mean, let's say, yeah, that's a possibility, I guess. But normally when you set this up, right, you set this up at the at the beginning of your code. But I see your point, you know, but you're assuming you have some kind of a while loop. So you mean there are multiple execution of this piece of code? You're saying is that what you're indicating?
Yeah, so what I mean is by like instead of like B, C, D all executing in a sequence, it was like B, C, B, and then D. And A started executing like before D even started because it thought like because semaphore was 0.
Yeah. Okay. Sure. Yeah. I mean that's if the code of process B gets executed multiple times, yeah. I mean the semaphore will be incremented. Yes, you're right. Yeah. I think I get what you're saying. So let's assume that here you only execute the BCD only once. Okay. I see your point that the process B, I mean, sorry, not necessarily process B, the code you have for process B gets executed multiple times, right? So then you could, each time you execute the code for a process B, the semaphore gets incremented once. So if you execute PB 3 times, then you will bring this semaphore back to 0. So A will be unblocked. That's what you're saying, right?
Yes.
Yeah. Okay. Yeah. Let's assume that you only execute process B, process C, process D once. All right. Yeah, that's definitely, you know, in this little example, I'm assuming that they all being executed once. Okay.
Thank you.
Yeah. Thanks. Good thinking. Is that oh, Eka. Sorry, I don't know how to pronounce your first name. So.
No, that's right.
All right. Okay. All right, so let's do another one, okay? Well, this one would be similar to the previous example. You know, let's say you have 3 threads. You know, you need to you know the threads. There are essentially before you take this operating system class, you need to fulfill the prerequisites for 237 and 330. Okay, how do you enforce that? Basically, it's the same thing. So you want to you can set one semaphore to control that, and that semaphore value can be initialized as 0, right? And not necessarily has to be 0, but normally you set it up to start with 0, and then in the 237 thread, you do signal as well as in the 370. And then in the 570, you do wait. Well, actually here, this example here, actually I used 2 semaphores. Sorry, so the previous example, I have 1 semaphore, right, to control this scheduling order. And in this example, actually, the proposed solution here, you can set up 2 semaphores, one for 237, the other for 370. So both of them are initialized with a value 0. And then you would signal each semaphore for 237 and 370. And then for 570, you would wait on the 2 semaphores. Okay, so here you could enforce, you would enforce that the execution of 570 will be after 237 and 370. All right, does this make sense? All right, so, okay, all right, so there's another scenario I want to quickly talk about here is that let's say we have this scenario. So we have Tom and John. They want to play tennis with each other. So Tom will be getting the tennis rackets. John will try to rent a tennis court. Okay, so these two events have to happen before they can play tennis, right? Because both Tom and John, they need to have a racket and a tennis court to be able to play tennis with each other. So how do we use semaphores to do this? Anybody want to give it a try? So you guys understand the setup here? So
you kind of do it?
Yeah, give it a try, Frankie. Yeah.
Wouldn't you kind of do it like how you were talking about the last example? So like,
yeah,
570 would be play tennis, 237, and the other class could be Tom getting the tennis rackets and John renting the court. So once you get those two done, then you can go play tennis.
Oh, okay, that's a good try. But here I want to say you have two threads here. Okay, there are no. So in the last example, you have three threads, right? Basically, you have 570 itself as a thread, and it needs to wait for 237 and 370, right? But in this example, in this problem, you only have two threads, Tom and John. And I want to make so both of them, they want to play tennis, right? But they need to get the rackets, and they need to rent a tennis court. So both those two events need to happen before they can play tennis. So so it's like Tom and John being two threads, right? They need to coordinate with each other to achieve so that they can eventually play tennis, right? So here Tom is getting the racket. John is trying to rent the tennis court. So how do we solve this? It's sort of like Tom has to wait for John to get the court, to rent the court, right? But John, meanwhile, also needs to wait for Tom to get the tennis rackets.
Couldn't you have just one semaphore that you just assign to someone first, so like Tom gets access to it, and then once he's done, John gets access to it, and then once they're both done?
Okay. Yeah, I think that may also work. Yeah, if you just use one semaphore, well, but the thing is that one semaphore probably, no, in this case, probably wouldn't work, because essentially you want to do what? You want to block both Tom and John before acquiring the rackets. Oh, sorry. Yeah, no, before. So you want to block Tom and John while they're each doing their own task, right? So Tom is getting the racket, and then getting the tennis rackets and renting the tennis court can happen at the same time. But these two things need to be fulfilled before either Tom or John can continue. So let's consider like using two semaphores here. One for what? One for acquiring the rackets. The other is for what? Is for renting the tennis court. But you guys, you guys Frankie and Eric, you were on the right track. So let's see how this can work. So let's say we have two semaphores set up for this, for solving this problem. So what are the initial values should they have? Remember, in the scheduling kind of use case, we want to initialize the semaphores to 0, okay? And this is how you do it for Tom and John, okay? So Tom is getting what? Is getting the rackets, right? So Tom would do signal on the racket semaphore that will increment what? That will increment this the racket semaphore to 1, right? And then Tom would try to wait for the cord, right, to be available, which John is trying to rent, right? So let's say Tom is being executed. So Tom will again increment the racket semaphore, and when Tom is executing the cord semaphore, wait, assuming Tom is being executed first, okay? And Tom will be blocked because the cord is not available yet, right? So Tom will be blocked and waiting there for the cord to be available, right? And then John comes in. John will signal the cord, increment, right? Increment the cord semaphore, right? And then John will try to wait for the racket to be available. So when John executes, the racket is already available now because the racket semaphore is incremented to 1, right? So John will not be blocked. So John rented the cord, and the rackets already were acquired by Tom. So John can just do play. And while the cord semaphore is signaled, and Tom will also be unblocked because Tom was waiting for the cord semaphore, right? And Tom can continue. So so if you execute Tom first, Tom will be blocked until John signals the cord, right? But if you execute John first, John will be waiting for the racket semaphore. So either way, they both will be coordinated, right? Right? But this would be a sort of a good solution. What about this, guys? What about this? You see here, in both Tom and John threads, I do signal first for the semaphore that it is trying to acquire. But what if I do it for Tom, right? What if I do cord wait first, and then I would signal the rackets? What's going to happen?
Wouldn't they be blocked because they're negative?
Right. You mean Tom? Tom could be. Let's say we have Tom and John. They do this first. They do wait first. Okay. Note that I just switched the order. Let me get rid of all these. Okay. So note here, I just did a little swapping on the order of the code. Okay. So before I was doing the signal first, then I do wait. But now I'm trying to do wait for the cord because Tom is not responsible for the cord, right? John is doing that. So Tom tries to wait for the cord first. Then it would signal the rackets. And John is doing the same thing. Will this work? Anybody can give me an idea? Yeah.
We would have a deadlock because both of them would be waiting for each other.
Excellent. Excellent. Yeah, that's exactly it. So potentially this could be a problem, right? So exactly as I just call you Eka if you're fine with it.
That's right.
So I could just mention. So Tom calls this wait first, right? And then John. So Tom would be waiting for the cord. John is waiting for the racket, right? Actually, most likely this will be ended up with deadlock. So Tom will never be able to do signal on the rackets, right? Because it's waiting on the cord. But John is waiting for the rackets, right? And John will not be able to do the signal on the cord, which is what Tom is waiting for. So we have a situation, what we call here is what? It's actually what we call circular wait, okay? It's like sort of circular wait. This is a terrible pain. Okay, anyway, so yeah, so I would suggest you guys do a little more practices on your own on all these, you know, so these are very interesting problems. And they're also very good test materials, okay? All right, so, all right, pretty much we're done with semaphores. So semaphores there, again, this is a quick summary. I won't go through them again. I basically talk a lot about them, all right? So let's move forward to see how we can, actually, I want to show you guys another example of how to use semaphores to solve another classic problem, coordination problem in deadlocks, okay? So let's quickly brief on the deadlocks concept. So in the architecture review, I gave you guys a quick introduction of, you know, how a potential deadlock can happen. So I use this example, right? You have 4 vehicles approaching a shared intersection right here, right? So they, this shared intersection can be occupied by all these vehicles at the same time, okay, which would be this case. So you can see if it reaches to this kind of a state, none of them can move further, right? They're all being blocked, okay? So, so what are the properties of a deadlock? Well, there are some standard definitions for a deadlock, okay? So a deadlock needs to have 4 kind of conditions, or you can say 4 conditions must hold for a deadlock to potentially happen. Okay, so what are those 4 properties? So first, the shared resource, you know, you can see here the intersection is the shared resource. That resource has to be mutually exclusive for either of these, for all these vehicles to access, right? So so you have mutually exclusive shared resources that are being accessed by multiple processes or multiple, in this case, multiple vehicles. Okay, and the second property of a deadlock is you have a hold and wait situation. Okay, like here, you know, each vehicle occupies, you know, a part of this intersection. Okay, but you know, for a vehicle to go through this intersection, it has to have, right? It has to have at least like for this one, right? Let's say this one is the vehicle 1. It needs to also have vehicle 2's, what vehicle 2 is occupying to get through, right? So anyway, so so you have a hold and wait situation, okay? At least one process is holding a resource and is waiting to acquire a resource held by another process, okay? So, and also, so we just talked about two properties. And the third property would be, there's no preemption here. So there is, say, there's no policeman here to coordinate everything. You know, in this, if you have a policeman here, it could, you know, it could order one vehicle to back up, and then so that another vehicle can go through. So, and the fourth property would be circular wait. Okay, so they're waiting on each other. All right. So how do we solve the deadlock problems? There are three general approaches that we could do to solve a deadlock problem. The first one would be sort of like you're trying to prevent the deadlock from happening, right? So it's like you're trying to write your code to impose some restrictions on the programs to prevent the possibility of a deadlock. You try to prevent this from compile time, all right? So that's what we call deadlock prevention, okay? And so that's compile time. So that's you try to write your program in a proper way to not let the deadlock situation happen, okay? And the other approach, it would be you're trying to handle this at runtime, okay? So there are two ways for handling the deadlocks at runtime. So one is what? One is that you already have a deadlock happening, okay? So that means you already entered this kind of state. Okay, they're all deadlocked here. So in that situation, you need to do what? Your program, your system needs to detect that situation, okay? Then do something with it. So that's what we call deadlock detection. So the system needs to find instances of deadlock so that the system can recover from that state, okay? And another runtime approach to deal with deadlock is the deadlock avoidance, okay? So you want to set up some algorithms at runtime. They could check the resource requests and availability at runtime so that those algorithms, they can be used to avoid deadlock at runtime, right? So essentially, the deadlock problem is still sort of a resource allocation problem. So you could have algorithms to try to kind of to try to figure out, you know, with all the ongoing resource requests and availability of these resources, then the algorithms can navigate between these requests and availability of resources to make sure that a deadlock wouldn't happen. So that's what we call deadlock avoidance. Okay? All right, let's say, let's try to use semaphores to try to deal with a deadlock problem. You guys probably have heard about this classic coordination problem. It's what we call dining philosophers problem. So the setup here is kind of straightforward. So you have 5 philosophers sitting on a round table. They could think or they could eat, okay? But for them to eat anything, they need to get 2 utensils, right? So that they can eat, okay? But the problem here is that you only have 5 utensils available, right? For 5 guys. When one guy is eating, it needs to have 2 utensils at the same time, beside him or her, that he can, you know, he or she has to have 2 utensils to be able to eat. Okay, so you could see that if each one of them acquires 1 utensil, then they will all be starved to, you know, to not be able to eat anything because they hold a resource and wait for another resource to so that then they can continue. Okay. So any question about the setup here? All right. So we just talk about, okay, so, you know, how to deal with deadlock scenario, right? There are two approaches at runtime: detection and avoidance. Let's say we try to design a program to prevent possible deadlocks here. We want to use semaphores to try to solve this, okay? That would be deadlock prevention, all right? So, so let's think about a naive implementation first, okay? So here, let's say we do straightforward, you know, we want, you know, so when a philosopher wants to eat, right, it would try to get the utensil on the left and the utensil on the right, and then you will start eating, right? And then after the philosopher finished eating, and then it would release both utensils, okay? Will this work? You guys are all following, right? Huh? All right, so this wouldn't work because it potentially, while you're here, right? Say you, one philosopher acquires one utensil to the left, right? And right before the philosopher wants to, tries to acquire the other one to the right, this process can get switched out, okay? So then the philosopher will end up with only having one utensil, okay? So that philosopher is holding one utensil, and so the philosophers beside this philosopher would not be acquire the utensil this philosopher is holding, okay, to be able to eat. So anyway, so this could end up with potential deadlock. All right, let's see how we can use the semaphores to solve this. So again, deadlock prevention would be to write your code to prevent a potential deadlock, right? So you want to impose certain restrictions on the program to prevent the possibility of a deadlock. So let's see how this can work here. All right. So first, let's see the conditions. Let's review the deadlock conditions again. That need to be satisfied for deadlock to potentially happen, right? So we want to so we talk about mutually exclusive access to multiple resources, in this case, the utensils. And we talk about the hold and wait property, right? And we talk about no preemption and circular wait. So here, a quick idea here is that this implementation I'm showing you here is trying to break, actually it's trying to break the number 2 condition, hold and wait, okay? So, so what would be the condition that, so first let's see, what would be the condition that would make a philosopher able to eat? What would be the condition? A philosopher, when a philosopher is able to eat, it would be what? It needs to acquire both utensils, right? On the philosopher, on the 2 sides of the philosopher at the same time, right? So the key idea in this implementation is to make sure when a philosopher tries to get utensils to eat, it needs to get both utensils beside this philosopher at the same time. Okay, so you either get 2 utensils at the same time, or you don't acquire any utensil. Okay, so we're trying to avoid the scenario that the philosopher only acquires 1 utensil and hold it. We want to break that condition. Right? You guys get the idea? All right, so we want to avoid what? Hold and wait, right? So that means, again, the philosopher, when philosopher wants to eat, it wants to acquire both utensils at the same time. Okay? All right, so let's see. So here, let's say we have, just very quickly, we have, we can set up 2 kinds of semaphores, okay? So I will go a little quicker here after you guys can look into the slides and for if you want to look more into this solution. So basically we want to set up, so we have the philosopher can have 3 possible states. Philosopher can be thinking, he or she can be hungry, right, and trying to eat, and the eating, and while the philosopher is holding the resources and eating. Okay, so and the mutex here is for protecting the access to the shared data. Okay, what are the shared data here? Utensils. Okay. All right, so we also want to have a semaphore for each of the philosopher, right? So this is for what? This is for enforcing the scheduling constraint, okay? Let's say we initialize the semaphore for each of the philosopher, for each philosopher to 0. We want to initialize the semaphore for each philosopher to 0. All right, so the general process is quite straightforward, right? So a philosopher will start thinking, and at a certain point, the philosopher would feel hungry, and the philosopher would try to acquire utensils first, and then the philosopher will can eat, right? And after eating, philosopher will release the utensils. Again, the key here is that what? In the take utensils step, as I said, you want to do what? You want to acquire both utensils. All right? You guys get the idea? You either acquire both utensils so that you will be able to eat, or you don't acquire any. Okay? So let's see. So the key function here is, the method here is to take utensils. Okay? So let's see how this works. So first you would guard this critical section, right? So, and once the philosopher gets into the critical section, it will set itself the state as hungry. Okay? Then it will do what? It will try to acquire. It will try to acquire both utensils. This is the essence of the idea I just talked about. So if the state of the philosopher is hungry, right? And what? And the utensil to his left and to his right, sorry, the stage of the philosophers beside this philosopher, they're not eating. Okay, you guys get the idea? So so if the philosopher, it wants to acquire both utensils, and he or she finds out the philosophers beside him or her are not eating, that means both utensils beside this philosopher are available. All right, you guys get the idea. Then under that condition, it will increment its semaphore. So that means it's available. Both utensils are available for this philosopher to use. Okay, and after that, this philosopher will what? Will try to decrement its own semaphore. Now, if this philosopher didn't acquire both utensils, then its semaphore will not be 1, right? You guys, this is the essence of this algorithm here. So only after this philosopher acquires both utensils, then its own semaphore will be incremented, okay, to 1, right? But once that happened, and then at the end of this take utensil, you will try to decrement this semaphore. What's going to happen? If you already have this semaphore at 1, if you decrement this semaphore, then the semaphore will become 0. Then that means this process will not be blocked, right? Because it's not less than 0. So that means what? This philosopher can continue to eat, right? This is because it has acquired both utensils. And then after that, it has its own semaphore incremented to 1. And then at the end, this decrementing of the semaphore will not block this philosopher. But let's say another philosopher wants to eat at the same time, and that philosopher, let's say a philosopher beside the philosopher just acquired the both utensils, and that philosopher just acquired who acquired both utensils, that philosopher is still eating. And another philosopher beside that philosopher wants to acquire the semaphores, the utensils to eat. It will be blocked because this condition will not be fulfilled. Okay, so that means another philosopher wants to eat. It will not be able to acquire both utensils, and then eventually it will be blocked at the end of this take utensils method. I know this is a little confusing. Has anybody followed for what I just said? Anybody? Is this part confusing?
Yeah, a little bit. Still trying to understand.
Okay. Anybody actually understood what I just said? All right, so I will let you guys look into this solution. So essentially, again, here, what we are trying to do here is that you either a philosopher, a philosopher will be able to eat is that this philosopher has to acquire both utensils beside him or her. Then the philosopher can go on to eat. Okay. If either one of the utensils beside him or her is not available, then this philosopher will be blocked. All right. And this is the release utensils part. So I wouldn't go through this. Okay. All right. So I guess we're done for this for today's class. I guess the next class we'll continue synchronization to talk about monitors, which will be the last programming construct we want to talk about for the synchronization for help solve synchronization issues. All right. Any questions?
You have office hours in like half an hour, right?
Yes. Yes.
Alright,
We'll be starting from 7:15. Yeah.
cool.
All right. Any more questions before I end today's session? No? All right. Okay. I will talk to some of you in the office hours then.
All right. Thank you.
Okay. Thank you.